Thank you for the introduction. So the first author has some problems to apply a visa to be here. So we are from the same group, so I just do the work to present the work. And I hope that I can do a good job to explain the work and to motivate you to read the paper and also convince you that this is an interesting paper. Okay, so let's start. So the title of this work is Achieving High Coverage for Floating Point Code via Unconstrained Programming. So first, let's take a look at the title because there are several concepts here. Achieving high coverage, which is obvious, for floating point code, which means the numerical programs. And unconstrained programming here, unconstrained means without constraint solving. That is, we don't generate any constraints. Programming here means mathematical programming, which specifically refers to minimize a mathematical function. Okay, let's start. So the goal for coverage-based testing is that we want to generate test input data to cover all branches of a program. The program can be complicated, for example, as we see in this example. So this is a numerical program. It involves floating point operation, and it also involves pointer operations and type casting and some bit operations, which makes this program a bit complicated. We want to cover all the branches in this program. So in order to do that, the two popular approach to achieve the high code coverage is via symbolic execution or search-based testing. So symbolic execution, we have several limitations. For example, the well-known path exploration problem. And also, during the symbolic execution, we will meet a lot of constraints which may be difficult to solve. And another approach is search-based testing. So first, you need to define the fitness function. It is very tricky to define a good fitness function. And then you need to employ some heuristic search strategies in order to get high code coverage. So here is our approach. Our approach is some kind of magic. We involve no path issues guaranteed, and also involves no constraint solving. We won't generate any constraints. So our approach is very efficient for testing numerical programs. So this picture gives us a general view of our approach. So in order to test a function foo takes x as its input. We will derive another function called foo_r. This function is those generated functions, and it has two properties. The first property, that is, for every input of the original program, this function is non-negative, which is greater than or equal to 0. The second property is that this function gets its minimum value of 0 if and only if there is an input x which covers a new branch in the original full program. So after we have this, if we can successfully generate a function foo_r with these two properties, and then cover a branch in the original program can be tested to minimize this mathematical function. So we will repeat this procedure until there is nothing to minimize. So this figure gives us the intuition of our approach. Here, the rectangle denotes all invalid inputs for the function f, while in the ellipse, it denotes an input x which can cover a new branch. And the constructed function foo_r denotes the distance between any input x and this good input that we want. So if the value gets 0, which means that the x is within this range and it will cover a new branch, this is precisely what we want. So this is the intuition behind our approach. And how can we do that? Then I will use this example to explain the key idea. So here we have the simple program. This is the control flow graph. The program contains 4 branches, and our goal is to have an input which can cover all of these 4 branches. So here is the magic. First step, how to construct this foo_r. So we will introduce a global variable called small r. The initial value of r is 1. And for each of the predicates in the original program, we will derive a new function called pen. And the pen is a function which I will explain it using this table. So the pen will return value and the value will be assigned to R for each of the predicates. So this is the for R. So after the construction, the original full program maps the input X to some values it computes. Here, the full R maps the input parameter X to this small letter R. So the next question is, what's the semantics of this pen function? So here, this pen function denotes these four parameters correspond to this line. That is line L0, and the predicate X is equal to 1. So you should not confuse that this is the pen function is a mapping from this vector to something else. It is not. The pen function is defined using this table, and it maps the domain of these 4 items to the domain of these 4 items. So the 4 items correspond to how many branches has been or will be covered. It can be empty set, it can be the true branch or the false branch or both branches. And each of these situations will be mapped to a value. For example, if nothing has been covered, the value will be 0. And if everything is covered, the value is the old value of R. If one of the branches will covered, we will introduce another helper function to define that, and we will describe it in the next slide. So this R helper function corresponds to the branch distance. So this slide explains the branch distance function. So it is basically a helper function to quantify how far A and B are from attaining the branch A OPB. So this is a binary operation, and A and B are 2 operands, and this is the operation. So the operation only contains equality testing and inequality testing. So if it is equality testing, then we define this function as this quadratic term. If it is inequality testing, then we define it using this conditional function. So that is all. That is all the magic. So next, I will explain this idea using a concrete example, also using this motivating example. So our goal here is to cover all the 4 branches. So first, no branch is covered, which corresponds to the initial setting. Then, which means that the value of R is 0, which means that any input will be the optimal input will be because the function gets minimized to 0. So we will choose a random value of the input. So in this case, we can choose 0.7. So then we feed 0.7 to this 4R. So, and we know that the program will take the first true branch, and the second will take this branch. And according to the construction of the helper function, the first predicate will be converted to this conditional function, while the second predicate will be converted to this quadratic term. So the value, the 4R takes X as input, and it returns the value of this quadratic term. We don't know the relationship between X and Y. We all know that it will return value of this. So this 4R becomes a mathematical function. Then we use some existing library to solve these optimization problems. So after that, we know that 4R will attain its minimum at point -3 or 2. Then we will choose one of them. Say, let's choose -3. And then we use -3 to test this full program. So after that, we will go to this branch. Now the 2 branches are covered, so it corresponds to this case. So the pen function will return the old value R. So that is the value here. And now the full R returns the value of this conditional function. And then we just use the the existing library to solve this mathematical optimization problem. And from this predicate, it is easy to know that the function gets to 0, the value of 0, if and only if X is greater or equal to 1. So the library returns, say, 5.1, and then we supply 5.1 to the original program, and it will cover another branch. So according to this criterion, then R is equal to R, which is 1, which means that we are done here, and we covered all the 4 branches. So this is the basic idea of this approach. So we realized our idea and we implement it in the LLVM compiler. And we use LLVM to do the transformation and implement it as our front end. And the back end, this is the mathematical optimization solver, is called the Bayesian hop. It seems to be an algorithm in mathematical optimization. Then we tested our idea on a real-world math library. So this library was originally developed by Zhang, and it is the reference library for Java 9's math library. And the library has also been widely used in MATLAB, JavaScript, and Android, and it heavily relies on branches. On average, each function has about 20 branches, and the max branches are over 100, which is fairly complex. So here, this slide shows the empirical result, and we test our approach, which is cover-me, against the traditional random testing and Google's well-known AFL fuzzler, and also UCL's Austin tool. So here is the result. We can cover more than 90% of all the branches in this well-known mathematical library in just 7 seconds. And compared with this AFL, we can cover about 20 more branches than AFL. And AFL is well known for its efficiency, and we can do it 10 times faster than AFL. And compared with the Austin tool, we can cover more than 40% of branches, and with speed up of several orders of magnitude. So that is about the experiment. To conclude, in our work, we propose a new transformation for testing numerical floating point programs. And the goal here is we want to achieve high coverage. And our approach is very efficient. For each input, our approach will compute a new input to cover a new branch. And we use unconstrained programming, which involves no constraint solving. And the key idea here is to minimize a derived function instead of solving this large number of test conditions or constraints in the original program. So that's all, and thank you.
So we have plenty of time for questions. Any questions? Okay, let's start here.
So nice talk, thanks. One question I have is floating point logic is slightly different than, or floating point algebra is slightly different than real algebra. And your program transformation is going from a executable program to a set of constraints over reals. So can you say...
No, not reals, over floating point.
Oh, they are over floating.
Yes.
Okay, in that case, I take it back.
Thank you.
Okay, cool idea. I have two questions. First one, do you have loops in this situation, or is it only like branches that like no reoccurring loops? And the second one, if there aren't no loops, it would seem that a constraint solver would be maybe slower but more effective at covering everything. So did you compare to that? So.
Okay, I think the question is about the loops. And so in this criterion, I think loop doesn't matter because in loop, every predicate also covers two branches. We are working with branch coverage, so I think, in my opinion, loop won't be a matter. Yeah, and then the second question, I'm not sure how efficient the solver will be for handling the loops, but in our approach, we will never worry about loops because everything will be converted to a black box mathematical function. We don't care about the loops. We just care about the output of this function and try to minimize this function. So I think, in my opinion, it will be efficient to solve these constraints in a traditional way. Yeah.
There was.
So what about things related to floating points such as NaN? So like if you have a constraint like x not equal to x, how will you generate a constraint for that?
You mean if there is a branch that I cannot cover?
Yeah, so if the branch is so x not equal to x becomes true only for nans. So if there is a branch, someone has put a branch to check whether the input has become nan or not. Will you be able to cover those branches?
If x is equal to x, I think, which means that you mean, is your question related to the instability of the floating point programs?
It's more about how do you handle branches related to nans, or do you handle nans at all in your approach?
Length?
Yeah, not a number.
I'm not sure.
So this is kind of what I was getting at. This is an artifact of floating point representation as opposed to real numbers, right? And it seems to be something which is not captured in the set of constraints that you're referring to.
I think this one will be finally. I'm not sure if this. I think this will not be an issue here. Sorry, I don't know this. Yeah. No.
Yeah, maybe let's take this one offline in particular because he's not an author of the paper. But there's another question here.
Okay. In your example, the condition in if statement only contains the only one comparison. So how about adding more class, like adding more variables x and y or something like?
So that won't be converted into so. So I think here the operation is only equality test and an inequality test. If there is x plus y, and then x plus y will be converted into that value. So the constraint will always be tested to this form.
All right. Are there any other questions? No? Well, then let's thank the speaker again. Thank you.
Okay.